Muy buenas tardes a todos. Mi nombre es Juan Moirano y en nombre de la Comisión de Microsísmica y Sísmica Pasiva, le doy la bienvenida a este nuevo webinar en el marco del ciclo de conferencias, cuyo lema es compartir experiencias y ampliar las miradas. Aprovecho para recordarles que este ciclo consiste en charlas multidisciplinarias que se están llevando a cabo todos los jueves a las 16 horas de este año con 6 ejes temáticos. Últimos descubrimientos exploratorios en la Argentina, un ciclo que ya está completado, exploración de reservorios Shale en la Argentina, magmatismo y sistemas petroleros, exploración offshore en el Atlántico Sur, microsísmica, que es este ciclo, y campos maduros. Este ciclo de encuentros tiene por objetivo crear un canal que permita la difusión y el intercambio de conocimientos con un enfoque multidisciplinario. Es así que pretendemos que funcione como un medio de comunicación eficaz entre colegas de las diferentes disciplinas que integran las geociencias y de todos aquellos interesados de las diferentes áreas de la industria. En el día de hoy, continuamos con el ciclo de microsísmica, la antesala del simposio de microsísmica y sísmica pasiva, que se llevará a cabo como parte del 11º Congreso de Exploración y Desarrollo, que tendrá lugar en el mes de noviembre de 2022. En este encuentro vamos a contar con una charla en la que el orador Darío Baturan compartirá conceptos generales y aprendizajes referidos al monitoreo de sismicidad inducida, haciendo foco en experiencias en cuencas de América del Norte. Antes de comenzar, en el nombre de la Comisión de Exploración y Desarrollo del IAPG, le doy las gracias a nuestro orador invitado por su predisposición para compartirnos sus experiencias y por el tiempo dedicado a esta charla. La presentación tendrá una duración de aproximadamente 40 minutos. Durante la misma son más que bienvenidas sus preguntas, que nos pueden enviar a través del chat al que pueden acceder a través del panel de su derecha. Al finalizar la charla, vamos a disponer de tiempo para que el presentador pueda responderlas. La presentación será en inglés y ustedes pueden hacer sus preguntas en español o en inglés. En el segundo caso, nosotros las traduciremos para Darío. A continuación, damos lugar a la presentación de hoy, que se titula Key Insights Gained from Induced Seismicity Monitoring in North American Shale Plays, a cargo de Darío Baturan. Darío Baturan, con más de 20 años de experiencia en el diseño, desarrollo y ejecución de proyectos de monitoreo sísmico en diversos lugares del mundo, dirige la unidad de negocios de monitoreo sísmico llave en mano de la empresa Nanometrics. Sobre la base de su extensa experiencia en la industria y en sismología, Darío enfoca su actividad en el desarrollo y producción de soluciones para monitoreo de sismicidad natural e inducida, adaptadas a necesidades que son críticas para el desarrollo de proyectos en las industrias del petróleo y del gas, minería, secuestro de carbono y generación de energía, entre otras. Darío impulsa la implementación de modelos innovadores de negocios asociados a desarrollos tecnológicos avanzados dentro de diversos mercados, con el objetivo de proveer productos con contenido de información geofísica clave para el manejo efectivo del riesgo sísmico y mantener la continuidad de los negocios. A partir de su ingreso a Nanometrics en 2002, Darío ha ocupado varios roles dentro de la organización en su camino a su actual posición dentro del equipo ejecutivo de la empresa. Darío tiene un grado de Computer Systems Engineering de la Universidad de Carleton y está basado en Ottawa, Canadá. Now, please, Darío, you can begin with your presentation.
Thank you for that introduction, Juan. I am just going to share my screen. Okay, I hope everybody could see my screen. So yes. Once again, thank you. Okay. Thank you for the introduction, Juan. And Juan has mentioned, the title of my presentation is Key Insights Gained from Induced Seismicity Monitoring in North American Shale Plays. Essentially, the content of the presentation is based on about 8 years of experience and being heavily involved in seismic monitoring across North America, Alberta, British Columbia, Oklahoma, Texas, Ohio, and other states unconventional oil and gas operations, and the associated issue of induced seismicity. So I'll start off with a very brief introduction. So induced seismicity is a very well-known phenomenon. There are many examples going back all the way to 1950s and 60s, whereby seismic activity can be triggered by man-made activities such as mining, dam impoundment, geothermal operations, sequestration, carbon capture and storage, as well as oil and gas injection activity. Over the last 7 to 8 years, there has been a significant number of seismic events that have been characterized as induced, that have been recorded in a number of shale plays in North America. Some of these seismic events or earthquakes have been high in magnitudes, which of course has brought on regulatory and public scrutiny. And in response to increased public awareness, there are a number of regulations that have been put in place to try and manage the risk of induced seismicity in a number of jurisdictions. And I'm going to touch on some of those regulations later on in the presentation. Some of these regulations and induced seismic problems essentially also resulted in an unprecedented volume of seismic data that has been recorded in these plays in North America. This has come from both densification of public seismic networks that are operated by national and state and provincial authorities, but also via deployment of complementary private seismic networks financed by operators, for example, that have, like I said, resulted in an unprecedented volume of seismic data. Having been involved with gathering and the analysis of this seismic data essentially forms the basis for the presentation and the slides that I will show today, and essentially forms the cornerstone of the themes that I'll be discussing. So the key insights I've kind of grouped around 5 basic themes, like I said, based on seismic monitoring experience in Canada and the United States. So number 1 is understanding the nature of the seismicity is key to managing it. I'm going to touch on different types of induced seismicity, and I'm going to touch on different types of activation mechanisms, as well as how seismic risk can vary between different regions and even pads. Very important point on recording seismic network. So one has to be careful about how seismic data is interpreted, and seismic data interpretation sometimes changes with the seismic monitoring resolution. In North America, all of the regulations are based on traffic light protocols that have thresholds that are set based on magnitudes. Magnitudes are a well-known seismology problem, and it is important to get them right because operational shutdowns have in the past depended on those magnitudes. There's been many suggestions from academic and other places that the regulatory protocols could and should be expanded to also include ground motions, so I'm going to touch on that. And then the final theme will be essentially, is real-time induced seismicity risk management possible? And the answer, as you will see, is yes, but it does include an investment in high-resolution seismic monitoring, which might be costly and thus not practical on all operations, but perhaps highest operations that are at highest seismic risk. So let's dive right into it with the first theme. So first, I'm going to talk about some of the key induced seismicity attributes. And I'm going to talk about 2 different examples over here. In the top right corner, what I'm showing is a map of seismicity recorded in a shale play in Western Canada that denotes seismic activity that is induced by hydraulic fracture operations. So if you look at the map here, the map shows seismic events that are geographically clustered very much around pads that were completed by oil and gas operators. And if you look underneath on the histogram that shows essentially the number of seismic events with time, you will see that the seismic activity in time increases during the hydraulic fracture operations, and then that seismicity essentially dies down in between these operations. So this is an example of hydraulic fracture induced seismicity, and there's a very close both temporal and geographical or spatial correlation to the oil and gas operations. And I want to just add over here is that the overwhelming, if not all, of the seismic events shown over here are very small in their magnitudes and thus could not be felt on the surface or could not cause any damage, but can be recorded by sensitive seismic instrumentation that was in place monitoring this region. So first, like I said, point under hydraulic fracture related seismicity, strong spatial and temporal correlation to hydraulic fracture operations. If we look at every one of these clusters, we would see that the Gutenberg-Richter frequency magnitude relationship B value would be close to 1. So 1 is the B value that we would expect to see in active tectonic regions with natural seismicity. So fault activation with induced seismicity is consistent with fault activation seismicity patterns in naturally occurring seismicity. Number 3, there was no baseline seismicity in this region prior to the commencement of the oil and gas operations. So there was no baseline seismicity. The seismicity itself is uncorrelated with frac stage times. So whenever we are completing a particular well, or when we're injecting fluid, we expect always to see certain amount of seismicity, because hydraulic fracturing by its very nature is injecting fluid at high pressure to try and create new fractures in the rock or enhance pre-existing fracture networks to increase the permeability of the target formation. So creating fractures in rock causes seismic events which can be potentially detected. But during hydraulic fracturing, if all we're doing is creating these new fractures, we would expect to see seismicity that's only within the times where we're injecting fluid. If we have induced seismicity that's related to fault activation, then that fault will continue to slip even between frac stage time. So that's one telltale sign of fault activation and induced seismicity. Fifth attribute is that the seismicity typically diminishes within hours or days after the operation's completion. So essentially, as the fluid injection stops and typically local stresses return to their equilibrium state, the seismicity dies down, and we can see very little to no seismicity in between hydraulic fracture operations. And then the last attribute would be presence of positive magnitude events. So again, hydraulic fracture operations by their very nature are designed to create cracks in the rock and increase the permeability that causes seismic activity. But this seismic activity are typically negative magnitude events that are very, very small. If we start seeing positive magnitude events, that essentially signals that there are larger surfaces, small faults or segments of the faults that have been activated that have started slipping, and they're resulting in larger magnitude seismic activity. Final thing I wanted to mention here is that in the bottom right corner, I'm also showing a different type of induced seismicity, and this induced seismicity was triggered by wastewater disposal operations. You can see that there are some differences in that seismicity. So number one, there is no close either temporal or spatial correlation to the wastewater disposal injection operation. So the seismicity is quite distributed in a region that has many wastewater disposal wells, and you can see that the seismicity occurs almost continuously. And essentially, this type of seismicity or induced seismicity is slightly different than the hydraulic fracture one due to the nature of the operation. So water disposal wells, typically we're injecting into different formations. Those formations are highly permeable by their very definition. The injection goes on over a very long period of time, which means that the fluid progresses much further away from the injection point and has a potential of triggering faults that are much further away from the injection point, which then might continue to slip even if the injection stops. So the lag between the seismicity and the operations is much longer and can sometimes be months, as opposed to hydraulic fracture induced seismicity, where it could be hours or days. The next point I would want to talk about is that in induced seismicity, we've observed typically two different types of activation mechanisms. So the first activation mechanism would be a stress transfer or a fast process. So if we look at the right-hand side, we have wells that we are injecting fluid at high pressure. We're stimulating a particular volume of rock, and there is a fault nearby that is critically stressed and optimally oriented to the regional stress field. And what happens now is that we have stress transfer from this volume that either enhances the shear stress along this fault or reduces the normal stress along the fault, and this fault slips. The slips along the fault result in seismic activity that we're measuring. And this type of activity is predominant in hydraulic fracture-induced seismicity. So there is no hydrological link between the stimulated rock volume and the fault itself. The fluid does not make its way to the fault. It's the stress transfer that triggered this activity. And as I'm showing in this histogram over here, the seismic activity is very high during the injection, but the moment the injection stops and the local stresses return to their equilibrium state, the seismicity dies down very quickly, and then it's not seen for the most part in the future going forward. Different type of activation mechanism would be fluid or pressure diffusion. So unlike in the first case, we're injecting fluid, but now fault is much closer to the stimulated rock volume, and there is a hydrological link between that volume and the fault itself, which means the fluid makes its way into the fault, lubricates the fault, pressurizes it, the fault starts slipping, and then we see seismic activity during the injection operation. In this particular case, one of the telltale signs of this activation mechanism is that once the injection stops, and there is even a flowback on this operation, the fault will most likely, because now it's been pressurized, will continue to slip, sometimes for weeks or even months following the flowback. So even once the injection stops, the fault may continue slipping, as is the case here, where we see the operation stop and the seismic activity continued for weeks or months after the injection. So this type of activation mechanism is typically observed in water-induced or water disposal induced seismicity. So two different mechanisms that result in two different seismicity patterns. The next thing I would want to touch on is interpretation of the data sets measured that are characterized as induced. So the first and foremost, when we talk about induced seismicity, what really matters are the very large magnitude events. The very large magnitude events are the ones that have the potential to either be felt or potentially cause damage. So when we look at induced seismicity, in order to have a very large magnitude event, we have to have a fault that's large enough that will, the slip along which will cause a large magnitude event. So the magnitude of the event is directly proportional to the surface along the fault that has slipped and the amount that it has slipped by. So in order to get very large magnitude events, we have to have very large faults as well. So then translating that to what I'm showing over here is two examples of the induced seismicity data sets, one of which shows clear fault activation, where then seismic risk is higher, while the other one does not show fault activation and seismic risk would be low. So on the bottom left side, what I'm showing is a well that was being completed. This is a Western Canadian data set. I believe this data set is from Alberta. And what we have here is color-coded stages as this well was being completed, and the dots represent the seismicity that was recorded by a local seismic network along this well. What you can see is that seismicity is not clustered around the wellbores. It's not following the frac down the wellbore. And there's almost no spatial or temporal correlation to the actual hydraulic fracturing stages. Instead, the seismicity is delineating a fault system that's trending in southwest northeast direction. Essentially what you can do is draw out these faults, which, by the way, as is typically the case in induced seismicity, are typically strike slip faults that are near vertical and do not show up very well on active seismic studies. So very often faults that are in close proximity to the hydraulic fracture operations are delineated through seismic activity during the operations, rather than being observed ahead of time on active seismic data sets. So because we have these faults and their surfaces are relatively large, we would expect to see larger magnitude seismic events on this data set, and therefore seismic risk in this data set is slightly higher. On the other hand, on the right-hand side, I'm showing a data set recorded by a regional and a local seismic network. And what I'm showing here is three different pads, but that are all telling the same story. If I zoom into those pads and I map pads in the actual wells, the white dots represent the seismic activity that was recorded by the regional seismic array, and you can see that it's dispersed, and I'm going to touch on seismic monitoring resolution in a minute. But what you can see here is also seismicity that is color-coded, which is the exact same events, but that were recorded by a high-resolution local seismic network. So if you look at this seismicity, you can see, first of all, it's tracking the hydraulic fracture completion down the well bores. All of the seismic activity occurs during the injection. And the B value for these data sets is quite a bit higher than 1. So even though we have higher magnitude events, once we zoom in, we see that this seismicity is essentially corresponds to probably activation of pre-existing secondary fractures that are not big enough to trigger very large seismic events. And therefore, even though they were recorded by the regional seismic network, the seismic risk along all 3 of these pads is different. So the seismic risk would be higher here than it would be in this particular case. So not all induced seismicity recorded by high resolution monitoring represents fault activation, and therefore the seismic risk is not equal in all of these instances. So one thing I touched on in this slide is I've shown a data set that was recorded by the local seismic array and a regional seismic array. So this is an important segue into my next topic, and that is essentially that the seismic monitoring resolution drives the interpretation of the data to a very large degree. So what I'm opening up here with is a table that essentially shows 4 different types of seismic networks that have been deployed in North American shale plays. And I'm trying to compare those networks in terms of their purpose and performance. So on the left-hand side, we have public seismic networks. So these are seismic networks that are operated by United States Geological Survey on a national scale, or Natural Resources Canada on a national scale, or Oklahoma Geological Survey, Alberta Energy Regulator, and so on a state or the provincial scale. So those are public arrays that have seismic stations that are spaced in tens or hundreds of kilometers. Their magnitude of completeness, which means the smallest magnitude at which their seismic catalog is complete, is typically between 1.5 to 2.5 on the Richter magnitude scale. And the location accuracy of those seismic events varies between 2 or tens of kilometers, depending on the density of the seismic stations. Regional seismic arrays have typically been deployed in very specific shale plays. The station spacing is typically tens of kilometers. Their magnitude of completeness is about 0.7 to 1.8, and the location accuracy of the events is between 500 meters to 1.5 kilometers. And then we have private local arrays. So these are very high density local arrays that are deployed over individual pads, typically during the operations, where stations are spaced anywhere 2 to 5 kilometers. And these arrays can record magnitudes down to 0.3, typically, maybe even 0.5 in some cases, with location accuracy in tens or hundreds of meters. And then at the extreme end here, there are the microseismic arrays, which really do not play a role in induced seismic monitoring. These are very dense arrays of geophones deployed over individual operations or downhole arrays, and their purpose is really to estimate the effectiveness of stimulation design and well spacing. So they are quite costly and not really applicable to the induced seismicity use case. These 3 types of arrays are. So as we go from left to right, the monitoring resolution increases. What is monitoring resolution? That means that we can detect more and more seismic events because we're detecting smaller and smaller and smaller magnitude events, and we can locate those seismic events with a lot more accuracy. So that's what the monitoring resolution. And how do we achieve that increased resolution? Well, we deploy more seismic stations and we deploy them closer together. So the more seismic station one has, the closer together they are, the higher the monitoring resolution, but also the higher the monitoring cost. So the public arrays, they're there really to record the largest magnitude events and essentially tell the general public, do we have an induced seismicity problem, and how big is that problem? The regional arrays are there to essentially be deployed specific to shale plays, and they're there to characterize the induced seismicity in more detail, as well as to ensure compliance with the regulations. And then local arrays, now you're talking about much higher monitoring resolution, are typically deployed to actively manage and mitigate induced seismicity risk in regions that have very high seismic risk. So all of these arrays work in a complementary fashion. They are not meant to replace each other, they complement each other, and they all have different purposes. They play a different role in induced seismic monitoring. So what does this look like? I wanted to show one example that would show the differences in data sets recorded between different seismic arrays. So again, what I'm showing here is a data set from Western Canada. And this is a data set that was recorded over a period of about a year and a half. On the left-hand side, I'm showing a data set that was recorded by the public seismic network. I think there were 7 or 8 stations, and the closest station was probably 30 to 50 kilometers away from this particular region that I'm showing here. During this time period, the public array recorded about 300 seismic events with magnitude of completeness down to 2.3. And what you can see here is essentially diffuse clouds of seismic events. So this is telling us we suspect that there is an induced seismicity problem in this region. During the same time period, there was a regional subscriber array that was operated to meet the regulatory requirements here, which had a larger number of stations that were more closely spaced together. So there were at least 7 or 8 stations within 50-kilometer radius of this pad. And here, that array now recorded 900 seismic events with magnitude of completeness down to 1.1. And you can already see here that from a diffuse cloud of events, we have now migrated into a much more clustered view of the seismicity because we've detected, first of all, more events, 3 times as many events, because now we're detecting smaller magnitude events, and we can locate them more accurately. And then on the right-hand side, we have exact same data, but this data was now recorded by a local seismic array of 5 stations. Actually, 4 of them are shown here. So these were specifically deployed in this region. And now we recorded 2,500 seismic events with a magnitude of completeness of 0.6. So we've detected many, many more events and are able to locate them much more accurately. So now we see the true picture of the seismicity here. We see that there are 5 different clusters. All of these clusters are associated with 5 different operations. So there's a different pad with wells at every one of these clusters. And what's interesting, we're now delineating actual faults that are responsible for the observed seismic activity. And what's interesting here is that the size, orientation, and seismicity associated with these faults varies from pad to pad, despite their relative close proximity of a few kilometers. So again, you can see what the data sets look like as the monitoring resolution and cost increase from left to right. So this is kind of a graphical representation of the table that I've shown in the previous slide. And then maybe another way of looking at exactly the same issue is if you look at the top right graph, what I'm showing here is the x-axis. This is the timeline during which the data set from the previous slide was recorded. And what you can see here on the y scale is the magnitude scale of the seismic events. And each dot here represents a seismic event that was recorded. So what you can see here is that the number of events, as the magnitude decreases, the number of events increases exponentially. And if we have a local seismic array, we can record all of this seismic activity. The moment you move to the regional seismic array, there are fewer stations. Essentially, all of this activity below magnitude 1 is not recorded anymore by the regional array. And if you move to the public array, all you're recording are the highest seismic events, which is essentially the tip of the iceberg in terms of the seismicity. So that's the magnitude view. And then event location view. If you wanted to see a comparison in locations, here I'm showing exact same events. Dark purple located using the local array. Light purple are those same events located by the public array. So you can see the events are a lot more scattered. Average event location shift is about 2.7 kilometers. And on the right-hand side, I'm showing exact same graph. This time I'm comparing the local seismic array with regional. And you can see they're starting to cluster more. They're coming closer, but they still don't match the performance of the local array. And the average shift in event location epicenter is about 1.5 kilometers. So I think these slides, again, illustrate the differences in recording data sets across different seismic networks and monitoring approaches that, like I said, have different purposes. The next topic I'd like to tackle is the topic of magnitudes. So I would argue that magnitudes are the single most important source parameter. So if we look at on the right-hand side, I've just included here an example bulletin that's published by United States Geological Survey for every earthquake that they detect anywhere around the world. And when you look at that bulletin, the most prominent value that's displayed for every earthquake is the magnitude of that seismic event. Magnitudes obtained very high prominence and became very important in induced seismicity problem in North America because the regulations that were put in place in response to the induced seismicity problem were all placed in the form of traffic light protocols. So those regulations were developed by regulators and essentially stated traffic light protocols where they were thresholds that were based on magnitudes. And if an earthquake above certain magnitude threshold was recorded by a public array and a private array, then operators had to take certain actions. And essentially, for example, in Alberta Energy Regulator mandated that if there is a magnitude 2 earthquake detected within the area, high risk seismic area, then an operator would have to put in place a mitigation protocol that they had agreed with the regulator prior to the completion. If a magnitude 4 earthquake happened in Alberta, then anybody within active injection operations within 5 kilometers of that magnitude 4 would have to shut down their operations. So again, the thresholds were defined in terms of magnitude. And just as an example, operational shutdown thresholds were in Ohio Department of Natural Resources, it was magnitude 2.5. Oklahoma Corporation Commission in Oklahoma set that at 3.5. Oil and Gas Commission in British Columbia in Canada set it to magnitude 4. And then Alberta Energy Regulator in Alberta set it to magnitude 4. So you could see that the thresholds at which shutdowns would occur or mitigation protocols had to be enacted varied from jurisdiction to jurisdiction. But magnitude's uncertainty is a known earthquake seismology problem. So how do I best illustrate that problem? Well, if you look at the bottom of the slide here, I am showing magnitudes detected for a very large seismic event that occurred in January of 2015 in Duvernay Shale play of Alberta in Canada. What I'm showing here are 5 different magnitudes that were computed using different magnitude scales by different organizations for that exact same event. So you can see that the magnitudes vary from 3.7 all the way up to 4.4. Why is this important? Well, because this is in Alberta and we know that the AER regulator has mandated a shutdown at magnitude 4, if we use the magnitude from spectral fitting moment magnitude and NRCan published magnitude, then the operators should shut down their operations. But we use USGS MB magnitude or PGC's moment magnitude from a regional moment tensor, then those operators don't have to shut down their operations. So getting the magnitude right is important because the difference, like I said, because the impact of getting it wrong is an operational shutdown, which is incredibly costly. So why don't the magnitudes agree? And what has been done about it in North America today? So there are really 4 reasons why such a discrepancy occurs in magnitudes. So number 1, there are different magnitude scales. So I will bring up as an example United States Geological Survey National Earthquake Information Center based in Golden, Colorado, has a worldwide seismic network, and essentially their mandate is to report and record every magnitude 4 or larger earthquake around the world. They utilize Bulletin Hydra software package, which has over 15 different magnitudes that are computed. So different magnitude scales were built for different use cases. They measure amplitudes in different portions of the event spectrum and are therefore suitable for different types of magnitude ranges, as well as recording regions and recording seismic arrays. So there are different magnitude scales. To get around this problem and avoid the confusion, the regulations in North America started mandating a particular magnitude scale, and that has been typically local magnitude scale. Problem number 2, even if we settle on a scale, so we say we're going to use a local magnitude scale, the actual equation used for magnitude might be uncalibrated. So the way that the earthquake magnitudes are essentially developed or calculated is you have a seismic station with a seismometer, you measure an amplitude at that station, but then you have to scale that amplitude with the distance of that seismic station to the earthquake hypocenter. The rate at which you scale back that amplitude, or that's called a distance correction terms, is directly proportional to the regional attenuation of the area where the earthquake was recorded. So every magnitude equation has a distance correction factor. In local magnitude equations, the default equation to use is, let's say, Hutton and Bohr. Hutton and Bohr equation has a distance correction factor that's based on attenuation in Southern California. So if that equation is applied in a region of the world, in Oklahoma or in Ontario, for example, where attenuation is different than that of Southern California, we're going to end up with an incorrect magnitude. So the takeaway here in North America, as I've mentioned on my first slide, there's been an unprecedented amount of seismic data recorded over the last 7 or 8 years in response to induced seismic problem. And that data has been used to calibrate local seismic equations in every region where they're applied. So the regulations specify magnitude scale, and then we have a calibrated magnitude equation specific to the region in order to get a correct magnitude. The third problem is probably the smallest one, and it occurred only in the beginning of the induced seismicity issue in North America, and that was inadequate instrumentation. So there were instances where geophone instruments, which are suitable for microseismic monitoring and detection of very small seismic events at very close distances, were also used to try and record induced seismic events, which are typically much larger in magnitudes and are recorded at much longer epicentral distances. The larger the magnitude of the earthquake and the longer the recording distance, the more energy that earthquake has at very long frequencies. And those frequencies, the energy of those low frequencies was not adequately captured by geophones, and as such, the magnitudes were underestimated. So the response to that has been to essentially mandate deployments of the broadband seismic instrumentation, which can accurately record to scale all of the energy associated with larger magnitude events, like I said, recorded at larger epicentral distances. And then the final item that I'll mention here is the differences in recording networks. So what I can say is that even if the magnitude scale has been defined, that the magnitude equation has been calibrated, and every array uses broadband instrumentation, there still might be differences in the recorded magnitudes if we have different arrays that are recording the same event. So magnitudes are event magnitudes recorded by every seismic station within an array and then averaged together to give us a single value. If the network of stations is different, recording a seismic array, and they're sampling different portions of the radiation pattern and recording ground motions at different distance ranges at different site applications, we might end up with different magnitudes between local, regional, and let's say public seismic arrays. This problem, for example, in Alberta, has been shared by a regulator mandating all of the arrays sharing data for very large magnitude events. So if there's a magnitude 4 event, then the regulator asks operators to submit waveforms showing the recording of that event so that the publicly available data and magnitude are correct, that the regulatory calls are based on, is recorded accurately. So data sharing is one way to get around this particular problem. But magnitudes do not tell the same story or the entire story. And the best way to illustrate that is by showing, if I can draw your attention to this map of North America here, that is essentially showing 3 different earthquakes, one occurring in California, one in Oklahoma, one in Virginia, that occurred at different times, but they've had comparable magnitude. You see 5.6, 5.7, and 5.7. So all 3 of these earthquakes had exactly the same magnitude. But those 3 earthquakes did not have the same impact on the surface. So the dots that I'm showing here, color-coded, essentially represent the intensity reported by the general public following these earthquakes using the United States Geological Survey Did You Feel It service that's available on their website. And the color coding essentially represents the intensity of shaking, which is a scale on 1 to 10. So what we can see here is that even though these three earthquakes had comparable magnitudes, their impact wasn't the same, because the earthquake in Virginia had a much higher intensity close to the epicenter and was felt over a much larger area than an equivalent earthquake in California or Oklahoma, even if we account for population density differences in these three regions. So that means that not every event was created the same. And what I want to explain here, then, the role of ground motions is at the bottom left corner. I have a very simplistic diagram which essentially shows the earthquake source. So this is a fault that essentially slips. It's the slip along that fault surface that triggers seismic waves, which then travel through the media and then are recorded as ground motions on the surface of the earth. So when we talk about magnitudes, magnitude is characterized as the actual source. But magnitude, it is the magnitude of the event, the depth at which the event has occurred, the attenuation of the media that the wave travels through, and the near site amplification terms that determine the ground motions up on the surface. And those ground motions are essentially determine the impact of that earthquake. So the impact of a magnitude 4 earthquake that happens at 2 kilometers depth is not the same as the magnitude or the impact of a magnitude 4 event that happens at 40 kilometers depth. Even though they've had the same magnitude, the shallow event will produce much larger ground motions than the event that occurred 40 kilometers, because its waves get attenuated as it travels towards the surface. So this is why ground motions play an important role in seismic monitoring. If you look at this table here, ground motions represented as peak acceleration and peak velocity recorded on the surface of the Earth by seismic stations are directly related to instrumental intensity, and they're directly related to perceived shaking by human beings and the potential damage. And it's the ground motions that are also referenced in seismic hazard, and seismic hazard is referenced then in as part of the design spectrum in building codes. So magnitude characterizes the source. Ground motion characterizes the impact of that event on the surface. So in North America, there is an example. There's only one example where ground motions were used in regulations, and it's a pretty interesting use case by Oil and Gas Commission in British Columbia. In seismically active regions, the regions that the regulator has delineated as being having high seismic risk, the regulator had mandated a deployment of an accelerometer within 3 kilometers of any active operation. And then at the end of that deployment, at the end of the operation, the operator would have to submit a report of all of the ground motions that exceeded 0.008 G. These ground motions, the accelerometer doesn't have to run in real time, and these ground motions are not used to drive traffic light protocols or make any regulatory decisions. These ground motions are strictly given to the academic institutions, and the academic institutions then use those ground motions to try and calibrate ground motion prediction equations, which essentially show how much do the ground motions decrease with distance. And of course, if there are seismic events with accelerometers right above them, then this allows us to record ground motions very close to the epicenter of the event, which is typically where public data sets are the weakest or have the least amount of data, but that's also where the seismic hazard is the highest. So I guess the question is, should ground motions play a role in traffic light protocols? Potentially. Like I said, there is an attempt with British Columbia to do that because, like I said, event magnitudes do not tell the whole story and cannot be used to measure the impact of the event. The ground motions are used to measure the impact, and those ground motions can be related to felt and damage thresholds and as well, and are referenced in seismic hazard analysis. But if one were to use ground motions, the implementation would have to be very, there are some unanswered questions in terms of how they would be implemented. So number one, which threshold should be used? Should it be a threshold at which an event is felt weakly, where there's light shaking, moderate shaking, or strong shaking? And then ultimately, where or how far from the epicenter? So the ground motions are applicable to the location into which we have a seismometer that recorded a ground motion associated with the seismic event. But of course, we have a limited number of seismometers. We don't have a grid of seismometers that is covering the region. So the areas at which we have actual ground motion readings are limited by locations at which we have seismic instruments. So then where, if we set a ground motion threshold, which ground motion threshold would it be? Where would we, which recording would we take at which instrument? Because every instrument will have a different recording depending on its different distance from the epicenter. And then if we wanted to use predicted ground motions, which we can do through calibration of ground motion prediction equations and generation of these types of max of ground shaking, should we use a predicted or accurate ground motion? So these are very tough questions, and I would say for this reason, ground motions are typically reported and are main part of seismic monitoring, but they have not been used to drive regulatory traffic light protocols. And the final theme that I want to cover today is essentially the topic of real-time induced seismicity risk mitigation. So the areas that have high seismic risk in North America have already been delineated. So I'm showing over here a plot of seismicity. The purple lines here delineate Duvernay shale play in Alberta, and you can see seismicity recorded over the last 5 or 6 years, I believe, here. So you can see areas that have a high risk of seismic activity. So they've been very well mapped. But within this region, there are many, many wells and pads. And if we zoom into that region, and that's what I'm showing underneath, we see that the conditions at every one of these pads are different. So the size of the fault, the orientation of the fault, the type of the fault, orientation of the fault relative to the regional stress field, relative to the wells themselves, the stress state, the proximity of the fault to the wells, the completion and stimulation design at every one of these wells, and the activation mechanism that I talked about earlier on, they're all different. They vary from pad to pad. That means that if an operator were to develop a risk mitigation protocol, which could include skipping stages, reducing pumping volume, reducing pumping pressure, pausing the injection or even flowback, one protocol or one mitigation protocol will not work across all of these wells because the conditions are different. So how will one measure the effectiveness of the protocol? Well, the answer to that is that you actually need a real-time feedback loop. So you need a high-resolution seismic monitoring network that can record data sets that could be used to evaluate the effectiveness of the mitigation protocol that has been put in place. This is an example of maybe 3 key components of such a system. So number one, you could use continually updated seismicity, maximum seismicity, and maximum magnitude forecasting models. So huge amount of seismic data has been used by researchers and academic institutions to develop models that essentially forecast the probability of exceeding different magnitudes and forecasting the seismicity. So these models have been developed and can play a role of risk mitigation dashboards. Number two, one has to have a high resolution 3-dimensional view of the seismicity recorded in the vicinity of the operation to see whether the seismicity is related to microseismic hydraulic activity or whether there is a fault that is activated somewhere close to the wells, in which case the seismic risk goes up. And then there is this view that essentially tracks p-value, magnitude of completeness, forecasted model, actual seismicity, as well as the injection parameters with time to see how all of those parameters change relative to each other. So real-time risk management, it is possible, it has been done, but my final slide essentially says that in order to utilize it effectively, one has to have high-resolution monitoring. So if you look at these published models for induced seismic forecasting, they were developed using very detailed, high-quality seismic data sets. I call them research-grade data sets. Well, that means that if those same models are to be used in real time to manage the seismic risk, then the data recorded by the seismic networks that's driving the models has to be just as good, which means research-grade data sets have to be generated in near real time. What does research grade mean? Well, that means they're generated fast, they're accurate, and they're complete. So on the right-hand side, you can see this type of a data set could not be used, while the data set right next to it could. If I don't have, because I have enough events located with enough accuracy. Underneath here, I have a frequency magnitude distribution, which has low uncertainty because we have plenty of events. Over here, we have very few events, so I have high uncertainty with my b-value and frequency magnitude distribution, and therefore my forecasting model will be off. Underneath, I'm showing a real-time data set with many false positives, which are removed by seismologists, let's say next day. That data set, again, will introduce too much uncertainty in terms of forecasting and is not suitable to drive these types of models. This type of data set is. So in conclusion, it is possible to actively manage induced seismicity risk, especially with hydraulic fracture operations. However, it would require high resolution seismic monitoring, which is costly and thus not potentially applicable to all plays and should be perhaps applied only to the high seismicity areas. And with that, I come to the final slide and just a quick summary of some of the key bullets. I would say that as I've shown, the seismicity has a very close both spatial and temporal correlation to hydraulic fracture operations and some of the characteristics of naturally occurring seismicity in active tectonic regions. But that's not the case with the water disposal induced seismicity, which has slightly different characteristics and is a problem that is harder to manage. As I've shown, there are multiple activation mechanisms. It could be stress transfer or it could be fluid diffusion. Seismicity patterns are different in both cases, and that there is a high variability in seismic risk from pad to pad. So just because we record large number of seismic events, that does not mean that the seismic risk is proportional to the number of seismic events recorded. We have to look at the seismicity patterns and see whether they reveal larger faults being delineated, which are capable of producing larger seismic events and therefore increase the seismic risk. Data interpretation, it often changes with monitoring resolution. So this directly relates to the concept of different types of monitoring. So I said public and private, regional and local arrays, they play a complementary role. And like I said, they're not competing with each other. They fulfill different purposes and work in synergy with each other. In North America, all traffic light protocols that are at the core of the regulations are defined in terms of magnitude-based thresholds. Again, magnitudes, there is uncertainty. That's a well-known seismology problem, but based on the experiences in North America, there is a way to solve that problem and get accurate magnitudes to drive those protocols. Ground motions could potentially enhance traffic light protocols, but because they have a direct relation to earthquake impact, but one would have to be very careful with implementation. And real-time risk management by operators is possible, but it requires high resolution monitoring and data sets and real-time feedback loop, which, like I said, is costly and might be suitable only in high seismic risk areas. And with that, I would thank you very much for your attention, and I'd be happy to answer any questions at this point.
Thank you very much, Darío. It's a very, very interesting presentation. Bueno, ahora abrimos la sesión de preguntas de esta tarde. Recuerden que las pueden escribir en la ventana derecha de su pantalla. Okay, we have the first question from Natalie Requena, which is, according to your experience, how far from the stimulated zone a large fault can be activated according to the stress transfer mechanism? Is it possible to activate large basement faults located hundreds of meters below the stimulated zone, assuming that there is no secondary faults that connect the stimulated zone with the basement?
That is an excellent question. I'm gonna say I'm just gonna go back to a slide that's maybe applicable here. I'm gonna say this, that majority of the hydraulic fracture triggered seismicity involved faults that were not in the basement, but were much closer to the stimulated zone. They were in the sedimentary. They were sedimentary faults. And like I said, those faults stopped slipping certain amount of time after the activation. I don't recall in my experience with hydraulic fracture induced seismicity basement faults being activated. But that, of course, depends on the distance between the target formation and the basement. I did see that the case might be different in wastewater disposal. Wastewater disposal in certain regions, the target formations when wastewater was disposed was much closer to the basement, like Arbuckle Formation in Oklahoma, which is highly permeable, much closer to the basement. And I would argue that the majority of the faults triggered there were basement faults, which resulted in larger magnitude events. So is it possible to trigger a basement fault with hydraulic fracture operations? Theoretically, yes. But in my experience and based on the data sets we've seen, it's very unlikely. And it's water disposal that's more likely to do so.
Thank you very much. I hope, Neptali, this answers to your question. I have some a question that is a bit basic, but may be interesting to hear your opinion on this. At which magnitude are events expected to be felt by human beings, and at which level could they potentially cause damage?
I think I'm just gonna switch my again screen because it's easier perhaps to answer over here. So that's I think that's where the difference between the source parameters and the impact of the earthquakes come into play. So typically, I'm going to say roughly seismic events that are between 2.5 and 3. So in that range, seismic events, if they occur shallow, are probably big enough where they could probably be felt by human beings. And then once you start getting 4.5 to 5, magnitude 5, seismic events are typically big enough to potentially cause damage. But again, the most important thing, the magnitude is only one parameter, because like I said, the magnitude 3 event that is at 2 kilometers depth might be felt on the surface, but a magnitude 3 event that's 40 kilometers under the surface will probably not be felt in the event. So it's not only the magnitude of the event, it is how deep has that event occurred, how fast are the seismic waves attenuated on their way to the surface, and what are the surface amplification effects that determines whether that magnitude event would be felt and whether it would cause damage. So overwhelming majority of seismic events cannot be felt by human beings and can only be recorded by very sensitive seismograph and accelerographs placed on the surface.
Okay, thanks a lot. Another very interesting question would be if by the experience in North America, have there been any operational shutdowns in the North American shales as a result of the regulations? And in cases that there were shutdowns, have the operators been able to restart operations?
That is a very good question. So yes, there have been operational shutdowns since the regulations have been announced, but there were very few of them. So I can recall in Alberta, I think there were only 2 or 3 instances where an event magnitude 4 or larger was triggered that caused an operational shutdown within 5 kilometers of that earthquake epicenter. And I think there were a few examples in Ohio, a few in Oklahoma. I'm not sure if there were any in British Columbia. So The shutdowns are pretty easy. They're very, very well defined in regulations. They say, hey, you trigger a magnitude 4 or larger event, anybody within 5-kilometer radius, they have to shut down their operations until further notice. What regulations have not been very good at is highlighting how does one restart operations. That is undefined. So it's essentially once the shutdown occurs, then the regulator and the operator would monitor seismicity. The operator would have to demonstrate how are they mitigating the risk of seismicity, and then they together make a decision whether that mitigation protocol is sufficient enough for regulator to lift the operational shutdown and for the operator to continue their operations. So I have seen all three examples. I have seen examples where operations were shut down and then restarted a few days or weeks after, and then the well was completed. I have seen restart of operations. I have seen operators abandon the well. So operators make a decision not to continue with the operation. You know, they've only completed half the well. They essentially say, we're done here. We're not going to complete the rest of the well. And I've seen instances where the regulators never lifted the suspension. There was an example I've mentioned there where seismicity continued for months after that particular operation. In that case, the regulator never lifted the suspension, and essentially that well was plugged and was never even flowed back, or was never entered production. So there were but I want to emphasize here, there are very few shutdowns. Ever since regulations have been put in place and active seismic monitoring started, the problem has been managed for the most part, where there were very, very few instances where such extreme action as a shutdown was required. So that's a tiny percentage of all of the wells.
Those examples you mentioned are always referring to hydraulic fracturing, or you are talking also about water injection?
Primarily hydraulic fracturing. In terms of water injection, I cannot say with certainty. I don't remember right now of any shutdowns, but what I do know is mandates that have been put in place by regulators to reduce pumping rates and volumes. So they would introduce regions where wells were continued to, allowed to continue to operate, but the regulators mandate a significant reduction in pumping rates and volumes. So that I do remember. I don't recall whether there were any actual shutdowns of the wastewater disposal well.
Okay. Here we have a new question from Luis Donoso, and he asks if there is a difference in magnitude, in your opinion, which one will be the best option as velocity model to determine the hypocentral parameters? Is a local model, a basin scale model, the company model, the regulatory authority model? Could coexist more than one model? Example, a local network model versus a regional model.
Yeah, so that is an excellent question. I think maybe even this slide might be more appropriate, because we have one seismic event, one of these dots that is recorded by 3 arrays. So the location of the array, the location of the seismic event is driven by seismic stations that recorded it, and the velocity model that was developed for that region. So this location is different from this location, is different from this location. So of course, this location here, the local one, has the best accuracy, because the more stations you have, presumably you have the best velocity model, you have the highest density of the seismic station, so you have the best seismic location. But when we look at the differences in magnitudes, this epicenter versus this one, the differences are small, 1 kilometer or 2. So when we adjust for those differences, the magnitude does not end up changing by much. The biggest impact on the magnitude really is magnitude scale that's chosen and the distance correction that's chosen. And that in North America today all regulations stipulate local magnitude equations, and they stipulate particular equation that everybody is supposed to use in order to compute that magnitude, so that everybody's using the same distance correction factor in that equation. And then because everybody uses broadband instrumentation, you end up with very small differences in magnitudes between public, regional, and local arrays. And those differences are typically just the locations of the stations that are different.
Okay, that's very interesting. So it's always a matter of standardization within the community.
That's right. At the beginning of this problem, 7, 8 years ago, there was a default magnitude equation that was being used in different regions and different magnitude scales. So everybody ended up with very much different magnitude. But the regulations progressed, where a local scale was mandated, an equation with a specific distance correction factor was mandated. Everybody's using broadband instrumentation, and that has brought the differences in magnitudes much closer together.
Okay, we had another question from Eliezer Naranjo, and he says, according to your work experience, during a hydraulic fracturing event and microseismic acquisition, what has been the minimum and maximum pumping rate for which you have obtained a seismic record? At what TVD of the well?
That so that is I would not be well positioned to answer that question. I think in terms of seismic data sets that we have recorded, they were recorded from anywhere. I'd say the shallowest formations were 1.5 kilometers down to 3.5 kilometers, and everywhere in between. That's been typically recording range. With a local seismic network, so not microseismic network, but local seismic network, looking at that depth range, we can typically record event magnitudes down to minus 0.5, I would say. Anything below minus 0.5, you really need a very dense microseismic network to record. I could not comment on the pumping rate or pressure because we typically do not have access to that data. That is data that only operators would have, so we don't have access to the operational parameters that are associated with the seismicity.
Okay, all right. Thanks. And I have another question, which is very interesting for us because the protocols and the regulations are on a very initial stage here. How have the operators adjusted to the new regulations, and what was the effect on the industry?
That's so. I would say if I look at the last 8 years in North America, have kind of have been a journey. In the beginning, large seismic events started showing up in some of these shale plays, and their increase was in time and space correlated to the unconventional reservoir development. But there was it took some time for everybody to get on the same page and essentially accept the fact that there was a correlation and a causal link between those oil and gas operations and the induced seismicity. It took a few years to get to that point. And really what helped everybody get to that point is just seismic data. As more and more seismic stations got deployed and more data sets got recorded, eventually the data set became so overwhelming that one could clearly draw the link between the injection operations and the observed seismicity. Once we reached that point, I'd say that the regulators, the operators, and the academia kind of aligned and said, okay, well, how do we manage, continue to extract oil and gas resources in a responsible manner? And that's where regulations came from. And then the response of the operators has essentially varied. In some cases, some operators essentially do the bare minimum required by the regulations. They subscribe to a regional array. They provide data sets when required. On the other end of the spectrum, there have been operators who have been proactively managing each and every pad in their seismic risk regions, and they've generated some absolutely mind-boggling, I would say, data sets over large areas. And then the rest of the operators have kind of worked everywhere in between. What I would say overall within the industry, managing the induced seismicity problem essentially became part of the operational preparation and planning. They put protocols in place and then started actively managing that seismic risk as part of other operational decisions they would make. So I'd say that it's been essentially acknowledged, accepted, and then everybody switched to an active management of the problem in concert with academic institutions and government regulation agencies.
Yes, it seems that this three-party communication, fluid communication, is really very important. Connected with that, this is another question I have is the data from private subscribers or local seismic arrays in North America shared with the regulators and the academic institutions to facilitate the research? How is that being managed there?
That's another excellent question. So the answer to that is yes. There is a lot of data sharing. As I've said, there are lots of very high, very dense, very rich seismic data sets that were recorded by operators in their private arrays, be it regional or local monitoring arrays. And in some cases, not in all, those data sets have been shared with the academic institutions. So I mentioned in real-time risk management section, essentially that there are currently, you can research them, there are multiple seismicity and maximum magnitude prediction models that have been published by various research institutions. Those models were developed using detailed data sets that were provided by the operator, right? So some of the data comes from the public networks, because of course that data is public, but then the operators donate data sets because what the operators get in return, of course, is a better the benefit of the research and understanding of the activation mechanisms, more solid mitigation protocols, because we're all working towards the same goal, and that is minimizing the likelihood of triggering large magnitude events. So very often, operators have recorded and then donated or shared seismic data sets with different academic consortia and individual academic institutions, and then they have even jointly co-published papers. So lots of examples of that collaboration.
That's very interesting. Here I have another question from we change the subject from Álvaro Salgado that says, thank you for your presentation. In your experience, what kind of seismometers or accelerometers would you recommend to deploy when implementing each mentioned kind of array? Or can you give us examples of instrumentation used in them?
Okay, so I'm going to speak in general terms. I'm not going to start mentioning the instrument names and so on, because I want to make sure that the presentation is non-commercial. So if we look at here, public networks, regional subscriber arrays, and private local arrays, public networks are typically not deployed to specifically measure seismicity associated with induced seismicity. The mandate of the public networks is to record all seismicity on either territory of a state or territory of the entire country. So this would be kind of observatory grade instrumentation. So they would typically be very broadband instruments because their purpose is to record local, but also regional and teleseismic seismicity, record all magnitudes, induced or natural. So very broadband instruments would be required. In regional and private arrays, you're essentially shrinking the area that is being monitored. Those arrays, their job is to monitor local seismicity associated with a particular operational source. So there you would use broadband instruments, but it would be a lower class of an instrument than the one that you would typically use in a public observatory grade seismic network, because the use case is smaller. So if you go from left to right, you would say that the cost per instrument and the performance of the instrument gets reduced. And then in microseismic arrays, you would only use geophones, which are very high frequency, and they're only meant to record very, very small seismic events, and they will clip and or miss energy associated with larger magnitude events. So very broadband, and then geophone in the microseismic case.
So we could say that regional and private local arrays use approximately the same instruments.
Yes.
And
yes.
The big differences are in the microseismic are in the public networks. Okay.
That is correct. And like I said, primarily because in public networks, the instruments serve multiple purposes. The regional and private, you're really focusing on local induced seismicity. The public networks, they have a much broader mandate. Therefore, they, the instrument has to serve multiple purposes.
We have another question, which is very interesting, which is, do operators share seismic data? What impact have the data shared from between the operators? From Marco Gardini.
Do you say, do the operators share data between each other?
Or? Between each other, yeah.
Yes. So right off the bat, so this regional, these types of regional arrays, these are typically subscriber arrays. So in this case, there's one array, that dense array that's deployed in a region, and then all of the operators subscribe to that array, so they all get access to the same data. So that's one model whereby all data is shared with everyone. But yes, I have seen companies deploy private local arrays, and if they're operating in adjacent regions and they could benefit from each other's knowledge, they would share data between each other to essentially build a more complete seismicity picture in an area where they operate. But the tolerance and willingness to share depends from company to company. That's been my experience.
Okay. And another one is, what role have academic institutions played in Canada and USA in managing the induced seismicity problem?
Well, like I said, they have been the beneficiaries of the data set. So they have primarily done research. The biggest outputs of that research, like I said, number one, have been the forecasting models that are published, tested, and can be used in real-time systems. Number two, the activation mechanisms. So slide number 2 that I've shown over there. So detailed study of the activation mechanisms so that the operators can understand how their operations could potentially trigger this seismicity, and then use that learning to redesign or adjust the operations to minimize the risks. Academic institutions have also financed or contributed some seismic stations to the public networks to increase the monitoring resolutions. They have published papers on changes in local and regional stress fields. So again, essentially multiple research topics that are then made public, but that benefit both general public and operators primarily, because all of that knowledge has been used to then adjust operations to minimize the risk of triggering larger magnitude events.
And connected with that, when the protocols are discussed and designed, have you seen interaction between the industry, the regulators, and the academia also?
Yes, what I have, in my experience in North America, I have seen the regulators rely on seismology and geophysics recommendations from the academic institutions when putting these regulations in place, especially in cases where the regulators did not have the seismology and the scientific knowledge. They would rely on academic institutions for inputs. as well there. So there has been a very good collaboration between academic institutions and the regulators on that front.
Yeah, well, I think that is something that can be very rich. Here we are trying to go that way. At least personally, I think that is the best way to go, to share all the knowledge and all the data, all the possible data. Okay, I think we don't have more questions, so we can finish with the Q&A session. Vamos a terminar con la sesión de preguntas y voy a pedir un comentario final a Darío. So Darío, please, we would like to, now we are going to finish with the Q&A session, and I just like to ask you to feel free to add any comments as a concluding remarks that you feel useful.
I think the last few questions actually summarize perhaps the best the point I would make. I mean, the issue of induced seismicity, like I said, it's been around for a number of years in North America, and even at the beginning of that issue, there was some skepticism and perhaps controversy in conversations. But that as more data became available, we could see the operators, the academic institutions, the regulators all converging on a common understanding and working much more in sync to try and manage the problem effectively, because the outcome and the goal is the same. It is essentially attaining that social license to operate, to responsibly recover natural resources. And I hope that some of the insights that have come from my experience and having been involved with that issue over the last number of years help Argentina and other places around the world achieve and attain that same goal.
Okay. Thank you very much for the presentation, and also for all the experience you transmitted to us. And okay, now we are going to finish with the session.